Ladies and gentlemen, welcome to machine learning. In this video, we will be talking about the maximum likelihood and the derivation of the linear least squares. Let's jump right in. Let's first talk about the maximum likelihood. We talked in the last video about that we want to find parameters, W's, so our weights, so that they fit the data as good as possible. So we want the best fit to the data. And now we want to say, well, how do we define what is the best fit to the data? To do so, we have to first jump from the deterministic view. So we have a function y is equal to f of x and w to a probabilistic view. So now we have the probability of y given our parameter or input x. So this is now a statistical model where y is a random variable. So to get this function, to get this statistical model, we have to add a parameter theta. So a fixed set of parameters, theta, which includes all the parameters of the deterministic model, these are omegas, and any other parameters to get to a distribution function. So we get our statistical model. And the goal is to set the parameter such that under the assumed statistical model, so this is our f of x with the w's, the observed data is most probable. So if we talk, for example, about a normal distribution, where we can define that the mean, for example, and we define the mean at 0, so this is at as x is equal to 0, but our data is at x equal to 10. So if we now get the probabilities of this data, we see that this mean is not very probable. So the most probable distribution, or the most probable mean, would be around 10. So around this area, so x is equal to 10. So the goal is to maximize our likelihood function. So we want to change the parameters of our function, of our probabilistic function, so that the probability of this data that we have occurring is most probable. So theta, ml, not for machine learning, but for maximum likelihood, is the vector that maximizes our probability of data given our theta. We can add a logarithm because a logarithm is a monotonically increasing function. So this is equal to the argmax of the ln of the likelihood function. Or if we talk about, or if we add a minus, we can say that we want to minimize this function. So a minus of the probability given a vector theta. And we will call this a error function. This might be a little bit too difficult to understand right now, but we will now derive the linear least squares and you will easily understand it. So now to the derivation of the linear least squares. We propose the following statistical model. So this is exactly the same thing that we had before, but now we have a noise term. So our observation, our labels, are a deterministic function plus some noise. So f of x is a deterministic function. For example, omega 0 plus omega 1, w0 plus w1 times x. This is our f of x plus some noise. And that noise term is everything that we cannot capture in our model. Because, for example, if we have a model, then this is our f of x, or maybe I should make a straight line. This is our f of x, but the data points are right here. So they are around our function. So this would be not true if we didn't have that noise term, but because of that, we have that noise term, we can say that this is how our function actually looks like. So epsilon is a noise term that describes everything that cannot be captured by our data, but by our function, so our model. Now, if we talk about least squares, we assume that epsilon is a zero mean Gaussian random variable with variance sigma squared. And now we can say that if we have this as a distribution function and we add a constant term to it, so we just shift the mean. So our probability of y given x is a Gaussian distribution with the mean equal to f of x and omega, w, sorry. So our probability of y given our sum x is a normal distribution of our result y with the mean of f of x and w given also a sigma squared, so the variance, sorry. And the expected value is still our function, so our basic statistical model that we proposed. This might be very difficult to understand like this, but as soon as you look at this picture, you will understand it. So we say that the probability of y, so this one, the probability of y given x is a distribution function for the mean. This is the mean. Given the mean is the blue line, so the mean is right here, and some sigma squared. So for example, if we say that this is or let's make a new graph. So this is a straight line. We say that the probability, if this is a function f of x is simply x, we say that x is at 2, y will be also at 2, and we would insert here a 2. So now we have a normal distribution centered around 2 with a standard deviation of sigma squared. And now with the help of that, we want to find the solution of the best parameters w. So again, to the likelihood function, we say that we want to maximize the probability of the data given our parameters. And if we write that out, so we have our parameters are x, so our inputs, our w's, and our sigma squared, where x is just a vector of our inputs and y is a vector of our labels. What we can assume now, or what we must assume, is that our observations are independent and identically distributed. So they are not correlating to each other. So they're not dependent on each other. And if this is true, so if they are independent, we have x and y is equal to probability of x times probability of y. We can say that the probability of our data, so of the whole data, is the probability of each event multiplied with all the other events. So this is the probability of x1 times the probability of x1 y1 times the probability of x2 y2 and so forth. So we multiply all probabilities together, a times probability of b times probability of c and so forth. So we multiply the probabilities, and the probabilities are our normal distribution. So we multiply the normal distribution with each other to get the overall probability of our data. Now, from that probability, we can take the log likelihood, because we said as before, the log is a constantly increasing function, a monotonically increasing function, and thus we can just simply have the logarithm. If we have a logarithm of, we have ln a times b, we can just say it's ln a plus ln of b. So we get from a product, we go to a sum. Because we know that our normal distribution is e to the power of minus and so forth, minus this one, we can just write it out. So we have the probability of, let's remove this one. So this right here is this one. So the probability of 1.5 times e minus 1/2 sigma, and the difference between the observed and predicted value squared. Now we can use again the rules of the logarithm, where we split these terms into two, where we get this term, the logarithm of a constant and minus this term. So let's remove this so you can see better. So this term is split into, we remove this square root and put it to a n over 2 because we have a sum to n, and we have again here the sum to n. This stays, but we factor out our 1 over 2 sigma and are left with just the sum of yn minus f of xn and w squared. Now we can again split this term into this one, and this stays the same as it was before. So we see that the likelihood function of our data is a constant minus a constant and is just dependent on this term. So in the future, we will have to focus on this term because this is also dependent on our w's to get the w's so that the data is most probable. So this error function that we just derived, I just rewrote it back here, is our error function. So we want to maximize this function, which is basically to minimize this error term, because if we subtract less, we will get more. So we want to minimize this function, and we call this now our error function. So we get 1.5 times the sum of yn minus f of x and w. Why do we have a 1 over 2 if we had a 1 over 2 divided 1 over 2 times sigma squared? Because if we later take the derivative, the prefactor doesn't matter. So this is just a simple constant. We have to focus on this part. That's why we can just remove that and add another constant. The error function would be the same if we had for example, a 22, or we had nothing here. The 2 will just help us later. So this is now our error function, and this is basically the least squares solution or the least squares method, because this function is just simply the squares that would arise when we plot our function and insert the difference from our predicted value and our observed value. So the goal is basically to minimize the L2 norm. So this is the L2 norm, which is the distance between the observed value, this is the value right here, and the predicted value of our deterministic function. This is our function f of x and w, and our observed values. And now we know how we got to our error function of the least squares. In the next video, we'll actually talk about how we can get those parameters w. I summarize again. So we introduced the principle of maximum likelihood. So the data is the most probable. From that, we said that we propose a probabilistic function with our deterministic function f of x and w and some noise that has a probability distribution. Then we said that if our noise has a probability distribution, our function is also a probability distribution. Then we said that our observations are independently and identically distributed. We said we take the log likelihood of our function, we use the rules of the logarithm and get to this expression that we are trying to minimize. So this needs to be minimized. And this is the sum of squares. So this is just simply the L2 norm that we try to minimize. I hope this video gave you a slightly better understanding into the topic of maximum likelihood and least squares. In the next video, we will talk about the analytical solution to this problem. If you have any questions, feel free to ask them in the comments down below. And thank you very much for your attention, and I'll see you next time.